Hello everyone, myself M. Shivaramedi and our team ID is G952 and our team members are Rishit, Irfan, Harsha and Nandish, and our project is crystal structure generation using an auto-regressive large language model, so which is an improved version based on the research paper called Crystal LLM. So we used a base research paper called Crystal LLM. And in this presentation, basically, we will look at the base research paper, then we will discuss the problems, and then we'll look at the solutions for those problems. And first, let us look at this base paper, that is Crystal LLM. And the main idea of this paper is usually large language models generate sentences or paragraphs. So like how we used chatbots. But in this research, the model is trained to generate crystal structures instead of normal text. So to do this, so we generally used to represent crystal structures, we use some format called CIF files, which stands for crystallographic information files. These files basically describe how atoms are arranged inside a crystal in 3 dimensions. So the model used in this paper is a transformer-based large language model. So, and it is trained using millions of CIF files, which are converted into text format. So one big advantage of this method is traditionally we used methods like density functional theory simulations, which used to take a large amount of time and computing power. So, but this method, which can generate thousands of possible crystal structures in just few seconds, and by just simply giving the chemical composition as input. So now let us look at the problems. So even though the crystal LLM model is powerful, it still has some limitations. So the first problem we identified is the data inconsistency. So the training data for the model comes from different sources and simulations. So because of this, the training data may contain inconsistencies or noise, and this can affect the quality of the model's learning, which can affect the model's learning. So this is one of the problem. And the second major limitation is a lack of property prediction. So the model can generate the structure of a material, meaning how the atoms are arranged, but it does not predict the physical properties. So it can just uh, generate how the atoms are arranged, but it can't predict the physical properties, and this is one of the another problem. So the project scope in our project, we will replicate the original Crystal LLM architecture using PyTorch so that we can understand how the base model works, and we will try to optimize this model. So we plan to improve the training data by adding something called conditional tokens, and these tokens help the model understand which dataset or computational method the data is uh, coming from, and this helps reduce confusion in the data and improves the learning. And we also plan to modify the model architecture by adding a regression head, and this adding component will help the model predict a numerical property such as formation energy. And to verify the generated crystal structures, we will use the PyMaintain library, which is commonly used in material science for analyzing crystal structures. And for example, we are not doing physical laboratory experiments, and we are not developing a web application interface. Our focus mainly is on the model and algorithm itself. And let us look at the solutions for the problems we discussed before. In the original model, the system only performs one task, which is generating the crystal structure. But in our approach, we convert the model into a multitask learning system. So the first improvement we introduce is the conditional generation, and in this we add special tags or tokens at the beginning of the input data, and these tokens help the model understand the source of the data and the computational settings used. This reduces the problem of data inconsistency. And the second improvement is a simultaneous regression. Here, we modify the final layer of the transfer model. Instead of producing only the one output, the model produces two outputs. So the first output generates the crystal structure in the text format, just like the original model how it used to generate, and the second output predicts a numerical property such as formation energy like we discussed before. So finally, the model can take a chemical formula as input and produce both the crystal structure and its predicted property at the same time. This makes the model more useful in the real world material discovery. And now looking at the base architecture diagram, first the input includes the chemical composition along with the conditional tokens, and this input is then passed through multiple layers of the transformer decoder network, and these layers allow the modern model to learn complex relationships between atoms, elements, and crystal structures. At the final stage, the model splits into two separate branches. The first branch performs token prediction, which generates the crystal structure step by step in safe format, and the second branch performs regression, which creates a numerical value representing a physical property of the material. And because of this design, the model can perform two tasks simultaneously, which are structure generation and property prediction. And summarizing this presentation and our project mainly focuses on applying large language models to the field of materials discovery. So we carefully studied the base paper, that is crystalline, and understood how it generates crystal structures using a large language model. And we identified two issues, that is data inconsistency and lack of property prediction. And to address these problems, we proposed an improved system called multitask crystal LLM, and which combines structure generation with property prediction in a single model. And so far, we have completed several initial steps. And in the next milestone, our goal is to replicate the base crystal LLM model and demonstrate a working version that can generate crystal structures on our local system. And thank you.